Welcome to the online course on pericyclic reactions and organic photochemistry. We are in module 27 of the 6th week. We are going to introduce the organic photochemistry from this module onwards. Let us in this particular module see some fundamental concepts related to photochemistry in general, specifically to organic molecules, photochemistry of organic molecules. Photochemical reactions are essentially reactions which are activated by photon energy. In other words, the activation is by light. The energy associated with the photon is transferred onto the molecule by a electromagnetic radiation molecule interaction kind of a process that takes place. The reaction involved are coming from the excited state of the molecule. Therefore, the electronic distribution is different from the ground state. In other words, the molecules that we are dealing with in the excited state are essentially electronic isomer of the ground state of the molecule. In fact, the electronic configuration is what is different about the excited state molecule compared to the ground state molecule. Unlike the thermal reaction, the photochemical reactions can be extremely selective in terms of the activation, because by suitably choosing the wavelength of light that corresponds to a particular species, one can activate that particular chemical species without affecting the other chemical species by light. So the selection of wavelength is extremely important for selective activation of a particular molecule in a mixture containing many starting materials. The events that are taking place in the photochemical reactions are as follows. The first event has to be the absorption of light. Without absorption of light, we cannot have a photochemistry. The primary photochemical process involved is involving the excited state, and then the follow-up secondary reaction, which are actually dark reactions arising out of reactive intermediates. So these are at least the three types of processes that would take place in any photochemical reaction. In this, we are not considering the photophysical processes. We will not pay much attention to the photophysical processes in this module. We will consider the photophysical process in the later modules. Now, there are a couple of laws of photochemistry which are essentially common sense kind of law. The first law is proposed by Grothus and Draper, and it states that only light that is absorbed by a molecule is effective in causing the chemical changes. This is fairly obvious, because if the photon energy is not absorbed, then there is no photochemical reaction. But the important aspect of this particular thing is that one should choose the wavelength of light that corresponds to where the molecule absorbs. In other words, it is absolutely essential to first record the UV visible spectrum of the molecule before photochemistry can be attempted for any kind of a molecule. So although it is a common sense kind of a thing, it is to be practiced properly. In order to do photochemical reaction, one need to first run the UV visible spectrum and find out where the molecule absorbs in the UV visible spectrum, and use the wavelength corresponding to a specific excitation wavelength corresponding to the absorption of the molecule in the UV visible spectrum. Now, the second law is proposed by Einstein and Stark. One quantum of light is absorbed by each molecule undergoing a primary photochemical photo process. In other words, in order to produce an excited state, at least one photon has to be absorbed. One quantum of light has to be absorbed. So as a corollary of this particular law, one can state what is quantum efficiency. The photochemical reactions are characterized by quantum efficiency, just like you would characterize the turnover frequency and turnover numbers in a catalytic process, for example, or the percentage yield in any organic synthesis, which shows the efficiency of that particular process. The quantum efficiency is essentially a ratio of the number of molecules reacted or the number of molecules formed divided by the number of quanta of light absorbed by the molecule. Ideally speaking, for every quantum that is absorbed by the molecule, if it undergoes a photochemical reaction, the quantum efficiency will be 1, because every excited state molecule produces one product molecule, or one reactant molecule is consumed to give a product molecule by one quantum of absorption of light. Then the quantum efficiency, because this ratio becomes 1, the quantum efficiency becomes 1. Oftentimes, the excited state molecule does not produce the product. The excited molecule gets deactivated by several photophysical processes that can take place. So the quantum efficiency can be much less than 1. The quantum efficiency can also be greater than 1 if the primary quantum absorbed by the molecule is producing a reactive intermediate, which is causing, for example, some kind of a chain reaction. So photochemical chain reactions, the quantum efficiency can be much higher than 1. So quantum efficiency essentially depends upon how effectively the excited state molecule that is produced is reacting in a photochemical manner to produce the product, or produce a reactive intermediate which will propagate the reaction by a chain process and so on. We'll come back to the quantum efficiency of photochemical process at a later stage with some examples, but this is a general definition of the quantum efficiency of any photochemical reaction. Now, in order to understand the photophysical processes, Jablonski devised a diagram which is represented in this particular picture. The y-axis is essentially a potential energy axis. The x-axis doesn't have any kind of a dimension or anything. It is not a reaction coordinate, or it is not an internuclear distance of any kind. Instead of drawing potential energy wells to represent the various energy levels, he simply adapted a flat diagram like this to describe the processes that are involved in the excitation process and the excited molecules undergoing various type of photophysical processes. Now, all the molecules, organic molecules, essentially stay in the ground vibrational state of the ground electronic state. The S0 is the ground electronic state, and the small lines that are drawn here in the ground vibration electronic level is essentially the vibrational level, starting from 0th vibrational level, first vibrational level, second vibrational level, third, and so on and so forth. So S0 and these lines essentially represent the ground electronic state with the vibrational structure associated with the ground electronic state. S1 similarly is the first excited singlet state, and S2 corresponds to the second excited singlet state. So the S essentially represents the singlet state, and the T represents the triplet state. So essentially this is the first excited triplet state with the corresponding vibrational levels that are shown here. Now the red lines are essentially the electronic excitation from the ground vibrational 0th vibrational level to the various vibrational levels in the excited state S1 as well as to S2. Now any excitation to corresponding to the S2 level will result in the immediate deactivation by non-radiative pathway, which is an internal conversion, resulting in the formation of the first excited state, which is the S1 state. So the S2 state rapidly decays back to the S1 state, and the other photophysical events essentially take place from the S1 level. Suppose if the molecule is excited to the various vibrational levels of the S1 level, before it can undergo any other photophysical processes, the excited vibrational levels will essentially come to the 0th vibrational level of the excited state according to Kasha's rule, and whatever the photophysical events take place essentially take place from the 0th vibrational level to the ground state of the molecule. What are the processes that can take place from the 0th vibrational level of the excited state to the ground state molecule? The first one is the wavy line that is shown, which is an internal conversion, which is nothing but dissipation of the excess energy that is present in the excited state to the surroundings by means of heat. So it is a non-radiative pathway kind of a process is what is taking place. The radiative pathway, of course, is known as the fluorescence, coming from the higher the 0th vibrational state of the higher excited state, in other words, the singlet excited state of the molecule, to the ground state, to the various vibrational levels of the ground state, which is S0. So the green lines that are shown here are essentially fluorescence emission lines. In addition to that, there is a possibility of the S1 state undergoing decay to T1 state, which is an intersystem crossing. This is a spin forbidden process. Essentially, it is a forbidden process because there is a spin change from singlet to the triplet state in this particular system. Nevertheless, several molecules do undergo the intersystem crossing by various mechanisms. Once it comes to the excited triplet state, from the excited triplet state, it can either undergo an emissive transition, which is the phosphorescence transition, which is shown in the magenta color, or it can undergo internal conversion by means of non-radiative decay pathway to the ground state, which is the S0 state. So the Jablonski diagram essentially explains the various excitation processes and the corresponding decay of the excited state, electronic state molecule to the ground state by radiative as well as non-radiative process. At this juncture, one should now characterize these processes by the time domain that is involved in the system. For the electronic excitation to take place, it takes place in the femtosecond or sub-femtosecond time scale. And for the fluorescence lifetime is essentially of the order of nanoseconds, 10 to the power 9 seconds. And the phosphorescence lifetime is of the order of seconds to several minutes or even days, for example. So this is the longest lived species in terms of the lifetime of the phosphorescence state or the T1 state. The reason that is taking such a long time is because the T1 to S0 transition is also a spin forbidden transition. So it takes place quite a long time for the decay of the molecule from the triplet state to the ground singlet state by means of either emissive or non-emissive process. Now, why are the lines drawn in the vertical direction in this particular way? This is essentially because of the Frank-Condon principle. What is the Frank-Condon principle? It's a principle which tells you the relative kinetics of the nuclear motion versus the electronic excitation process that is taking place in a molecule. Now, the nuclei are heavier than electrons. A proton is about 1000 times heavier than the electron. So, the electronic transition from one orbital to another orbital takes place quickly, where when the nucleus is essentially stationary, in other words, there is no internuclear distance change during the electronic transition. The electronic transition is essentially much faster than the nuclear motion. In terms of time scale, if you look at the electronic transition takes place in the femtosecond time scale, 10 to the power minus 15 to 10 to the power minus 16 seconds, it takes place. Whereas the nuclear vibration, in other words, the interatomic distance changes take place essentially in the sub-picosecond, which is 10 to the power minus 13 to 10 to the power minus 14. In other words, it is at least 2 orders of magnitude slower than the electronic excitation is 2 orders of magnitude faster than the nuclear vibration in terms of the time scale that is involved in the system. You can also state the Frank-Condon principle in another way. The most probable transition between electronic states occur when the wave function of the initial vibrational state most closely resembles the wave function of the final vibrational state. This is something we will see in the next diagram. Now, what do we mean by singlet state and the triplet state? These are essentially to deal with the magnetic moment or the spin orientation of the 2 electrons that are involved. Let us state the ground state configuration is like this, where in the S0 state there are 2 electrons, and this is the lowest unoccupied molecular orbital, and this is the highest occupied molecular orbital of the molecule, let us say. Now, during the electronic excitation, without change in the spin, this is spin paired, and this excited state also spin paired. If you look, not spin paired, but the spin orientations are in opposite direction, for example. This is the singlet state. So, in other words, the multiplicity is retained in going from the singlet 0 to singlet first excited singlet state of the electronic transition that is taking place. In order to go from the excited singlet state to the triplet state, which is shown here, there has to be a spin inversion. As you can see here, this is downward to upward inversion is what is taking place. What do we mean by the orientation of the 2 electrons? In the presence of an external magnetic field, the number of eigenstate that it can exist are only 1 in the case of the singlet state, because essentially the magnetic moment is essentially 0 in this particular case. In the presence of an external applied magnetic field, the 2 electrons that are in opposite direction essentially undergo precessional motion, and not only they undergo precessional motion in the same frequency, they are also in phase in terms of cancelling the magnetic moment vector that is created by the 2 spinning electron. So, essentially the overall magnetic moment is essentially equal to 0, because this is pointing in the aligning with the external magnetic field, this is pointing opposed to the external magnetic field. So, the net magnetic moment essentially cancels each other to give the net magnetic moment of 0 in the S1 state. So, there is only one state that is possible, where the 2 spins are in opposite direction and they are synchronous in terms of their precessional motion in the presence of an external magnetic field. On the other hand, when the 2 spins are parallel to the external magnetic field, there are 3 possible orientation that it can take place. The 2 spins, both of them can be parallel with respect to the external magnetic field. This is one state called the T plus 1 state. The 0, plus 1 and minus 1 are the 3 eigenvalues to which the magnetic moment vectors can be, magnetic quantum yields can, the magnetic orbital momentum can be described in this molecule. The 2 spins can be pointing in the same direction, aligning with the external magnetic field, or they could be pointing opposed to the external magnetic field, which will have the highest energy, or they can be pointing, one pointing up and one pointing down in this manner, this particular manner, essentially not cancelling the magnetic moment vector as in the case of singlet state, because these 2 spins are precessing in different frequencies. They are not in phase with respect to each other. So, the magnetic moment vector in the direction opposing the external magnetic field and aligning with the external magnetic field are not equal in this particular case. So the net magnetic moment is still persisting in this one. The singlet to triplet transition essentially take place when the two spins are in phase or out of phase with respect to the precessional motion in the presence of an external magnetic field. So this essentially in a very qualitative manner describes the spin multiplicity of electronic states in an excited state, singlet state and triplet state of the molecules. Now this is a diagram which essentially shows the potential energy diagram. You can see here going from this position internuclear, this is a x-axis is internuclear distance here and the y-axis is potential energy. So essentially during an electronic transition, because of the Frank-Condon principle, there is no change in the internuclear distance. So vertical lines are drawn for electronic excitation as well as the fluorescence emission in this particular case. What this diagram shows is the various vibrational levels of the ground state and the vibrational levels of the excited state, and the density function is what is plotted in terms of the electron density. Probability is what is being plotted in this particular instance. So if an electronic excitation is taking place from the zero vibrational state of the ground electronic state and ends up in the second vibrational state of the electronically excited state, you can see here this is reaching the highest probability density, starting from the highest probability density. So such a transition would be having the maximum intensity in the absorption emission spectrum. Similarly, from this position also, it's from the highest probability density, it is coming back to the highest probability density in the 0 to 2 transition, which is the emission transition. So the excitation and the emission of 0 to transition is the highest probability transition. So that will have the maximum intensity of fluorescence emission and absorption in terms of the intensities that are directly proportional to the probability densities of the electrons in this diagram that is shown here. One can also see here this is a fluorescence emission spectrum and this is an absorption spectrum drawn in the blue. The 0 emissions are essentially matching with each other and the rest of the peaks are essentially looking like mirror image with respect to the 0 transition. In other words, if you look at the right hand side, the blue transitions are essentially looking like a mirror image of the green transitions which are shown on the left hand side of the molecule. What is the reason we have a mirror image with the overlap of the 0 transition? This is explained in this particular diagram. This is S0 state with vibrational level 0 to 7 and this is S1 state with vibrational level 0 to 7. And these are the excitation processes where electronic excitation take place. In other words, these are the vibrational absorption, these are the absorption wavelengths of the excitation process that is involved going from the ground state to the electronically excited state molecule. So that this is a 0 excitation and this is a 0 excitation. In between you have 0 1 0 2 0 3 so on, that is represented by the red arrows in showing here. Once the molecule reaches the excited state to the various vibrational level, remember according to Kasha's rule, they have to come back to the 0 vibrational state of the excited state. In other words, they have to come to this particular level before they can undergo emission process. This is because these vibration levels are so closely spaced, a thermal deactivation process in terms of internal conversion can take place quite readily, and that is what promotes the internal conversion to come to the 0 vibrational state of the excited electronic state. From the 0 vibrational state, now it can come to the ground state to the 0 level, first level or up to the 7th level as indicated by the blue arrows. Now if you look at this 0 transition, which is the excitation process, and this 0 transition, which is the emission process, these two energy levels are essentially same. That is the reason in the picture the 0 levels are essentially matching, overlapping with each other. This is a spectrum of anthracene. This is absorption spectrum on the left hand side and the emission spectrum on the right hand side, for example. The 0 transition of the absorption and the 0 transition of the emission are nearly overlapping with respect to each other. There can be some polarity, solvent polarity effect and so on, which can shift the 0 band of the absorption from the 0 band of the emission to various levels. This is called Stokes shift. In this case, very minimum amount of Stokes shift is observed because it is recorded essentially in a non-polar solvent. What is important is the mirror image relationship that one can see very clearly of the absorption spectrum to the emission spectrum. This is 0 this is 0 1 0 2 0 3 0 4 0 5 and so on of the various vibrational fine structure, and this vibrational fine structure in the absorption spectrum corresponds to the excited state vibrational fine structure, and because it essentially coming from this process of excitation to various vibrational levels, so absorption spectrum gives you information about the excited electronic state, whereas the emission spectrum gives you information regarding the vibrational levels of the ground state. So this is 0, 0 of the ground state, 0, 1 of the ground state, 0, 2, 0, 3, 0, 4 and so on of the ground state. The vibrational level is what is reflected in the emission spectrum. So this diagram essentially describes the mirror image relationship, explains the mirror image relationship. It also explains the Stokes shift. If it is a very highly polar solvent, specific solvation of the excited state or the ground state can essentially affect the upward transition from the downward transition, which will result in large Stokes shift in the case of highly polar solvent, which can specifically solvate either the excited state or the ground state depending upon the polarity of the excited state and the ground state. The type of electronic transition in organic molecule essentially depends on what kind of molecule that we are dealing with. If it is a saturated molecule, where you have only sigma electrons, then there is only a possibility of sigma to sigma transition that is possible. Let us take the example of methyl iodide. The Ci bond has the lowest energy absorption. So if one excites CH3I using a visible light, in fact if we leave it in room light, iodine is liberated essentially because electronic excitation causes the Ci bond sigma electrons to go to the sigma star electron. Once the electrons reach the sigma star, the bond order is essentially 0. That would correspond to the dissociative state of the CH3I, and it releases CH3 radical and iodine radical. The iodine radical essentially dimerizes to give iodine. So such is the photochemistry that is occurring because of the dissociative sigma to sigma star process that is taking place in saturated molecule. But the most interesting photochemistry essentially takes place in unsaturated compounds such as olefins, ketones and so on, which have pi electrons as well as lone pair of electron. If you take ethylene for example, it can undergo excitation from pi to pi star level, and this is a pi star transition of the olefin or the diene or aromatic compounds for example we talk about. On the other hand, if we take acetone, which is a ketone, it can undergo n to pi star excitation. The n to pi star excitation is essentially happening in unsaturated carbonyl compounds, unsaturated imines, those compounds which have a heteroatom with a lone pair of electron, which corresponds to the n electron in the molecule. In saturated system like ether, sulfide and so on, the n to sigma star transition is also possible because the heteroatom in the ether or sulfide or a phosphine can essentially give the electron from the the non-bonded level to the sigma star level. Again, a dissociative transfer of electron is what is taking place during the excitation process. Most of the cases we are going to deal with the pi star and the n pi star transition. That is what deals with most of organic photochemistry. Occasionally charge transfer transition is also involved. We will discuss the charge transfer transition in a separate module. So typically these two transitions are taking place in the spectral region of 200 nanometer to 600 nanometer region, which is a UV visible region of the organic photochemistry, where these two transitions are involved in terms of their energies. Now there are selection rules on the electronic transition. There are two types of selection rule. One is based on the spin, which is called the spin based selection rule. Transition between electronic states of the same spin multiplicity is allowed. In other words, if you go from a singlet state to singlet state or from a triplet state to triplet state, they are spin allowed transition state. However, going from a singlet state to triplet state or the triplet state to singlet state are spin forbidden. This is what I mentioned when I talked about the intersystem crossing from the excited singlet state to a triplet state. There is a spin change that is taking place, so that is a forbidden transition according to the spin selection rule. On the basis of symmetry selection rule, transition between orbitals of same symmetry is allowed, whereas transition between orbitals of different symmetry is forbidden. So this is something we will deal with a little later. Typically in olefinic compound, the pi to pi star transition is an allowed transition, whereas n to pi star transition is a forbidden transition because of the selection rules that we talked about in this particular slide. Now, in order to understand the photochemical processes that are involved, photochemical reactions, the processes that are involved in a photochemical reaction, this diagram will help quite significantly. Let us start with the reactant R. it is undergoing a photoexcitation process by means of absorption of a proton, and it goes to an excited state. So R star is the excited state of the molecule. From the excited state molecule, it can go to an intermediate stage, which is a reactive intermediate, for example. This is the primary photochemical process that can take place. In other words, the absorbed photon energy is now converted into chemical energy in transforming the excited state, electronically excited state molecule to a reactive intermediate. This reactive intermediate can be either a radical, or it could be a biradical, it could be zwitterion, it could even be a carbene, and so on. So there are several different types of reactive intermediates that can be formed from electronically excited state. It is not necessary the electronically excited state molecule should always undergo a unimolecular transformation. It can react with another molecule which is in the ground state to produce this kind of reactive intermediates. This is a productive photochemical step that is involved in converting the photon energy into some reactive species which can further undergo formation of the product. So this is a subsequent thermal reaction is what is taking place in converting the reactive intermediate to the final product. It is not necessary that every reaction should undergo via an intermediate formation. There are reactions which the excited state directly undergoes to go to the product in a unimolecular fashion or in a bimolecular fashion, depending upon the kind of interaction that exists in the transition state, and these are called concerted processes. Remember, concerted processes, photochemical processes, are where an electronically excited state molecule directly goes to the product without involvement of any kind of an intermediate, and hence this arrow corresponds to a concerted process. Now the energy wasting process is a photophysical process which are internal conversion, intersystem crossing, fluorescence emission, and phosphorescence emission. The former two are the radiationless transition, whereas the latter two are the radiative transition, which are photophysical processes. The excited state, electronically excited state molecule essentially loses the energy, goes back to the ground state. So this is an energy wasting process. All the processes which are photophysical processes are energy wasting, whereas the photochemical processes are the one that increases the quantum efficiency of the overall photochemical process that is. Therefore, the efficiency of the photochemical reaction depends on the competition between the energy utilizing photochemical step to the energy wasting photophysical steps that are involved in this. If this is extremely active in terms of the process that takes place, then the quantum efficiency will be low. If this is going to be extremely efficient, then the quantum efficiency will be very high for that particular photochemical reaction. So this diagram essentially in a very simplistic manner explains the processes that are involved in a photochemical step. Now within the processes, there are two types of process that can take place. The excitation can be either through a singlet state. Once a singlet excited state is formed, it can go to a reactive intermediate and then go to the product, as explained in the earlier slide. The reactive intermediate can be again excited to a reactive intermediate, which is an excited intermediate from which the product can be formed. This is a double photon excitation process. Seldom, it's not a very common occurrence that you have this kind of a process taking place. Most photochemical reactions are directly arising from the primary photo excitation process, which results in the R star. R star goes to an intermediate and then goes to the product. Now, without going through an intermediate, there can be a funneling process that can be taking place, where the Frank quantum minimum of the reactant molecule, in other words, the lowest energy point of the reactant reactant potential energy surface, touches or crosses the product potential energy surface, thereby converting the reactive intermediate to the product, which is a tunneling process, which is a funneling process actually, which is essentially equivalent to a concerted kind of a process, because there are no reactive intermediates formed in this particular step. So this is a process that involves the electronically excited singlet state. One can also have an electronically excited triplet state from which the reactive intermediate is formed. Once the triplet state is formed from the singlet state via the intersystem crossing process, depending upon the efficiency of the intersystem crossing, the triplet quantum efficiency can be either very high or low. It depends on the intersystem crossing efficiency. From the triplet state, the reactive intermediates can be formed. From the reactive intermediates, the products can be formed. So this is a process involving triplet excited state. There is a mistake here. This is not singlet excited state. This is a singlet excited state, whereas this is a triplet excited state process that is taking place in this case. Now let us define what are photosensitizers. Photosensitizers are molecules that directly absorb the photon energy and transfer the energy to another molecule which is a starting material for the photochemical reaction, and in the process the photosensitizer essentially quenches back to the ground state of the photosensitizer. In other words, this is purely an energy absorbing and energy transmitting molecule. It does not undergo by itself any photochemical reaction. It is almost like a catalyst, except it is not catalyzing the reaction. It is only promoting the transfer of energy from the photon energy to the other molecule. Simply put, it is an energy capturing and transferring agent. That's all a photosensitizer is all about. Photosensitizers can be either a singlet type of sensitizer or it can be triplet type of sensitizer depending upon the spin state of the sensitizer. Typically, alkenes and aromatic systems, which are pi to pi star transition systems, will act as singlet sensitizer. In other words, their intersystem crossing efficiency is extremely low. On the other hand, ketones and certain type of dye molecules like the methylene blue, rhodamine, and so on, they undergo the n pi star excitation. In some cases, because of the heavy atom, they also undergo the intersystem crossing with a high efficiency, and these are typically triplet photosensitized. For example, benzophenone or anthraquinone, they are all very good triplet sensitizers because their intersystem crossing efficiency of the n pi star state is very high. So hence they are the triplet sensitizers. How does the sensitizer work? Sensitizer essentially absorbs the energy, goes to the first excited singlet state, which is the excited state of the sensitizer. From the excited state of the sensitizer, it interacts with the reactant molecule, transfers the energy, and in the process the excited state reactant molecule is formed and the sensitizer is regenerated. Once the reactive excited state of the reactant is formed, it can undergo photochemical as well as photophysical processes as described in the earlier slides. This is a diagram which tries to explain the relative energy requirements of the sensitizer and the reactive molecule. Let us say, for example, this is the energy gap of the ground singlet state and the excited singlet state of the sensitizer. Upon photoexcitation, the singlet to singlet excitation takes place. This is the configuration, electronic configuration of the singlet exciteds of the sensitizer. S stands for the sensitizer and number 1 stands for the singlet excited state of the number 1 star represent the singlet excited state of the sensitizer. Now this is the electronic energy levels of the reactant molecule. You can see here the reactant molecules has a lower energy so that it can receive this electron from this higher excited state. In other words, this is the transfer of energy in terms of this electron hopping onto this level and one of this electron hopping onto this particular level. These are all spontaneous processes, as you can see, going from higher energy level to the lower energy level. So when the sensitizer comes in contact with the reactant molecule, it essentially transfers the energy. In the process, it regenerates the sensitizer and it results in the formation of the excited state of the reactant. You can see here by a simple electron transfer process, you can explain the transfer of the singlet energy from the singlet sensitizer to the singlet energy of the reactant in forming the singlet excited state of the reactant by means of a simple mechanism like this. So this is a photoexcitation process. This corresponds to the energy transfer process, regenerating the sensitizer molecule and producing the electronically excited reactant molecule in this particular case. The same kind of a mechanism can be applied for a triplet sensitizers also. The sensitizer undergoes excitation to give the singlet excited state of the singlet excited state of the sensitizer. High efficiency of intersystem crossing in certain molecules produce the triplet excited state of the sensitizer molecule. When it encounters the R, which is a reactant, the reactant triplet is produced, forming the ground state of the singlet excited state. So there is a spin conversion here. This is a spin forbidden process. This is a spin allowed process going from a triplet state to a triplet state. Once the triplet state of the reactant is formed, it can undergo photochemical and photophysical processes as the case may be. Now the primary photochemical processes that are typically initiated by excited singlet state is from the pi star state is concerted pericyclic reactions like a 2+2 cycloaddition reaction, for example. Reaction characteristic of carbonium ion and carbanion, which are photoionization processes which takes place in the singlet excited state. Cis-trans isomerization of the pi system, which also isomerization, that is a spelling M should come before E. So this is the cis-trans isomerization of olefins that can undergo from the pi to pi star excited state. They occur from the singlet excited states. And the electron transfer process can either take place from the singlet excited state or triplet excited state. The primary photophysical processes, chemical processes that can be initiated from the triplet excited state, in other words, typically from an n pi star excited states, are hydrogen atom abstraction, which typically comes from a triplet n pi star excited state, electron transfer processes, addition to unsaturated bonds, for example, homolytic fragmentation processes, alpha cleavage, and so on and so forth, and rearrangement of more stable carbon-centered radicals. This is something we will see during the course of the example. So these are the processes that can take place from a triplet excited state of a molecule. The kind of reactions that are going to see in the future modules are, for example, the photochemistry of alkenes, which would involve isomerization, which is cis-trans isomerization, cycloaddition processes. We are going to concern only about non-concerted cycloaddition processes because we have already seen the concerted cycloaddition processes in earlier example. Certain rearrangements also we will see, just like the dipymethane rearrangement is one example of an alkene isomerization. Photochemistry of carbonyl compounds essentially deal with alpha fragmentation, gamma hydrogen abstraction, and photochemical reduction of ketones and so on. The enones and dienones cycloaddition process and rearrangement process in the photochemistry of enones and dienones. The photochemistry of alkyl nitrates, we will talk about fragmentation and recombination, which is known as the Barton's reaction. Photochemistry of aromatic compound in terms of skeletal rearrangement and cycloaddition reaction. Photochemistry of N-haloamines in terms of fragmentation processes and recombination processes. Photochemistry of alpha diazoketone, we essentially talk about production of carbene and nitrogen from decomposition of diazoketones. Finally, photochemistry of singlet oxygen, we will talk about addition reaction, ene reaction, and oxidation reaction. We will also talk about photoelectron transfer reaction, which is a separate category of reaction which we will deal with in detail at a later stage. Now, the resources for these particular photochemistry modules are the book by N.J. Turo, Ramamurthy, and Scaiano. This is Modern Molecular Photochemistry of Organic Molecule, a very recent book. Exhaustive information is available in this book. It's a fairly bulky book to read, nevertheless highly informative book. Many examples are taken from this particular book. Calvert and Pitts' book, Pitts is a very classical photochemistry book. It's a very old book. It is out of print, probably not easy to get this particular one. Ninomiya and Naito, this is purely for synthetic purposes. They describe photochemical synthesis, published in 1989. And this is the book I am talking about this particular book, Ramamurthy, Turo, and Scaiano. This is a very useful book for this particular course. I hope you enjoyed this introductory photochemistry lecture. Thank you very much for your kind attention.